So it's important to be able to classify ODEs so that we know how to approach them, because different methods will be appropriate for different types of ODEs. So the first classification we're going to talk about is ordinary versus partial differential equations. Ooh, very strange E's. Okay, so ordinary versus partial differential equations. So if you're familiar with the difference between an ordinary derivative and a partial derivative, then that basically explains this classification. So let me just give a few examples, and we'll see some of these later. So there's the logistic equation, which is used for studying populations and other things as well, but its major appearance in the world of modeling is in population studies. Simple model. So the population size changes at some rate that's given by the current size of the population. And here we're going to write it as 1 minus population over what's called the carrying capacity. So this is an ordinary differential equation because there's a dp dt. And now, because I only have a prime and there's nothing else indicated, we're sort of able to sort of infer that the derivative is with respect to time, and there are no other types of derivatives in an equation of that form. Okay, so another one, this is one that you may not be, well, I guess it doesn't come up in very first encounters with differential equations, so I think of this as a less commonly seen equation, but in engineering, especially mechanics, this would, and civil engineering, this would come up. So the beam equation is an equation that describes the bending of long slender beams. So imagine you have like an I-beam or a 2x4, or in the cellular context, a microtubule or an actin filament, and you would solve an equation like this, where E times I characterizes the stiffness of the beam. W is the deflection. So if this is your beam as a function of x and it's been bent under some force, then this distance here would be W. The height, or the amount it's been deflected away from a flat line, would be W. And Q is the force profile being applied to the beam. And now you can see here we also have derivatives only with respect to one variable, the x variable, and this is the beam equation that I've got here is a static beam equation. In other words, it doesn't describe the dynamic motion of a beam. If we did have the dynamic motion of the beam, we'd have a time and a space derivative in the equation, but we don't in this case. So both of these are ordinary ODEs. And now let's do some examples of partial differential equations. So the heat equation, sometimes referred to as a diffusion equation, depending on how you interpret the function u, we have the time derivative, how quickly is the heat or the chemical concentration of something changing with respect to time. That goes on the left-hand side, and that rate of change locally in space is determined by the curvature of that profile, or the second derivative at least, which is an approximation of the curvature, which is a derivative in space. So you can see here we have a derivative in time, and here we have a derivative in space, and those two together in this way will give us a solution that describes the change in heat profile or the change in the distribution of a chemical, let's say dissolved and diffusing in water. So another equation, the wave equation, which can be used to describe the movement of deflections in a tight string, like a guitar string, for example. And the two-dimensional version of that equation, of the equation I'm going to write down here, is used to describe, for example, the vibrations of a drum head. The 1D equation is also a simple model or a simplified model of the propagation of electromagnetic waves through space. So let's see what this equation is. We take two derivatives of the object that's propagating. So if it's a guitar string, it would be the deflection on a guitar string, or for the case of electromagnetic waves, it would be the intensity of the electric field. And we take two derivatives with that quantity with respect to time, and that will be equal to c squared, where c is actually turns out to be the propagation speed, and then multiplied by two derivatives of the quantity with respect to space. So in both of these equations, we have a derivative with respect to time, and you'll notice one is a first derivative, the other is a second derivative. We'll talk about the way to classify that difference in terms of the order of the equation. And here we have a second derivative in both cases, a second derivative with respect to space. So these, because they have partial derivatives, the function u, it doesn't say it explicitly, but the function of u is a function of x and t. Whereas up here, w was just a function of x, and here p was just a function of t. So these ones are PDEs because they include both, in this case, space and time. But anytime you have an equation that has derivatives with respect to two distinct independent variables, you would call that a PDE. Okay, so that is the ordinary versus partial differential equation distinction. The next thing we can talk about is the order of a differential equation. And this is just the order of the highest derivative that appears. And so let's say for the heat equation, du dt, oh, those should be partial derivatives, du dt equal d squared u dx squared. We would say this is first order in time and second order in space. You could call it a second order differential equation because the highest derivative is a second order derivative, but that misses the subtlety that there's a different order in space and in time. So we usually emphasize that. And then for an ODE, for example, like the logistic equation, p prime is equal to r times p 1 minus p over k. This is just a first order equation. And you could say in time, but because there's only one variable, that's kind of redundant. Okay. So let's see, what is, I want to just give you a minute to think about this. What is the order of the beam equation? So EI equal dx squared, whoops, no, dx to the 4 equal q. And here, q and EI are just parameters, so they're just fixed. Actually, it doesn't really matter. The order of this will be the same either way. So I'll give you a second to think about that and commit to an answer in your head. Okay, I'm hoping you're there. So I'm going to just tell you now, this is a fourth order ODE in space. But again, we don't always mention that. So the wave equation, we would say second order in time, second order in space. Okay, so the last topic that I want to talk about with respect to classifying DEs is linearity. And this is actually a bigger and, in some sense, more important topic. So I'm going to leave that to a later video, subsequent video, the next one on the playlist.